Good morning, students. Welcome to the lecture of Operation Research. In the last lecture, we have started a new point of constructing Kuhn-Tucker conditions for solving a quadratic programming problem. In detail, in the last lecture, we have discussed what is or how to construct, how to derive the Kuhn-Tucker conditions. To derive these conditions, we have started with the quadratic programming problem, and this whatever the constraints are given to us, including the non-negativity constructions, non-negativity restrictions, we will convert all the constraints to equalities by having the slack variable of square type, that is qi square and rj square. Once we construct the equality constraints, then we will go for constructing a Lagrangian function. Once the Lagrangian function is constructed, how we are constructing this? Multiplying the constraint equations by the Lagrange's multiplier. For the original constraints, we will use the Lagrange's multiplier lambda I. That of for the constraints of non-negativity restrictions, we will use the Lagrange's multiplier mu j. We will multiply this, and these multiplication we will subtract from the original objective function. This is what an elaborative idea. After constructing this Lagrangian function given by equation number 1, we will go for forming the necessary conditions by Lagrangian method. How to do this? We will differentiate the Lagrangian function partially with respect to all the variables and equate it to 0. Here we have seen what is the derivative of Lagrangian function with respect to original variables xj given by equation number 2, differentiation of L with respect to lambda I given by equation number 3, L with respect to mu j given by 4, L with respect to qi and rj given by 5 and 6 respectively, where the equations obtained by 5 and 6 can be further simplified to equations 7 and 8, which is actually lambda I is equals to 0 and mu j xj is equals to 0. If we're looking at all the conditions we have obtained 2, 3, 4, 7 and 8, these are the necessary conditions obtained for solving the given quadratic programming problem. Wait a minute. Okay. Then whatever the conditions we have obtained by 2, 3, 4 are the linear equations in the variables except condition 7 and 8. Therefore, now the problem is equivalent to solve these equations. Okay, equation number 2, 3, 4, 7 and 8. Therefore, now what we will do, we will solve these equations generated by 2, 3, 4, which are actually the linear equations in the variables, subject to or which satisfy or by taking these conditions 7 and 8 into the consideration, right? Therefore, whatever the conditions 7 and 8, which are the non-linear equations in the variables lambda, mu and s and x, these are called as the complementary slackness condition. Therefore, we have seen the problem now becomes equivalent to finding the solution of set of linear equations which also satisfies the additional conditions lambda si equals to 0, mu j xj is equals to 0. Now, as the function is strictly concave, condition becomes sufficient. Now, in today's lecture, we are going to understand the Wolfe method, where the Wolfe method is designed or derived by using the Kuhn-Tucker condition. Mathematician Wolfe has given the systematic procedure of solving this quadratic programming problem. Let us start by Wolfe method. Mathematician Wolfe has introduced this method. Therefore, the name is given in his honor. Therefore, let me write again the quadratic programming problem. What is the quadratic programming problem? Maximize z is equal to f of x, which is equal to summation j equals to 1 to n cj xj plus half times double summation j equals to 1 to n k equals to 1 to n cjk xj xk. This is my objective function which are subject to the constraint which are subject to the constraints. Now, what are the constraint inequalities we have? Summation j equals to 1 to n aij xj less than or equals to bi and xj greater than or equals to 0. What the parameter I takes the values 1 to, yes, the parameter
M.
I takes the values, yes, it is 1 to m, j takes from 1 to n. Okay, what is one more property of the CJK coefficients? Yes, what is the property of the CJK coefficients?
Cj equal to Ckj.
Yes, where CJK equals to CKJ for all J and K, and the right hand side constants Bi are greater equal by 0 or non-negative for I equals to 1 to m. This is what the quadratic programming problem under our consideration. Okay, now we will go for the Wolfe iterative procedure. Wolfe's iterative procedure. Let us go stepwise. What step number 1 tells us? Now step number 1 tells us convert all the inequality constraints. Okay, inequality constraints means including the non-negativity restrictions. First we will convert this non-negativity restriction to less equal format, and then introduce the slack variables qy square in the ith constraint, rj square in the non-negativity restriction, and convert it to equalities. Convert the inequality constraints, convert the inequality constraints into equations by introducing slack variable variables qy square in the ith constraint, again let me write I running from 1 to m, and slack variable. What is the slack variable we were using for the non-negativity restriction? Rj square, no? Rj square j equals to 1 to n in jth non-negativity restriction. So this is the first method we have seen in which we were treating the non-negativity restrictions as the constraint. Actually, those are the constraints, but we were not taken the constraints into the calculations. But this is the first method in which we were converting the non-negativity restrictions also in the equality form. Okay. Now, what is the step number 2? In the second step, we will construct the Lagrangian function. Construct Lagrangian function. How should we construct the Lagrangian function? As we have seen in the last lecture, this is the function x variable q r lambda mu. Okay, and this is constructed as f of x minus multiplying by lambda I to every parameter, multiplying by lambda I to every constraint, summation j equals to 1 to n aij xj plus qi square minus bi, summation I is running from 1 to m. Okay, and later summation j equals to 1 to n mu j into minus xj plus rj square, minus xj plus rj square, where what is this vector x? Vector x is an n-tuple vector of the original variables x1 to xn, right? Q vector is the collection of all squared slack variables q1 square, q2 square up to qn. m square, right? What is r? R is r1 square, r2 square up to rn square. What for lambda? Lambda is lambda 1, lambda 2 to lambda m. And what for the last mu? Here only I will write. What is mu? This is mu1, mu2 to mu n. Okay. Next is what we were going to do. We were going to differentiate the function L partially with respect to the components of the variables, components of x, q, r, lambda, mu, and equating to 0, and equating the first order partial derivative to 0. First order partial derivative to 0, and we derive Kuhn-Tucker condition. Now, yes, in the last lecture we have seen in detail how to derive the Kuhn-Tucker conditions. So, for in today's lecture we are going to use the conditions directly. Kuhn-Tucker conditions. Now, let us go for step number 3. Now, in step 3, Wolfe role starts. Now, what Wolfe has done, actually solving this Kuhn-Tucker conditions is nothing but solving the system of linear equations, and which also satisfies the additional non-linear condition. Therefore, if we just look at all those linear equations, let me show you again these equations given by 2, 3, and 4. Now, in the simplex method, we have seen whenever we are going to solve the system of linear equations, one should start with initial basic feasible solution. For this, one should have an identity matrix in your simplex table. But if I look at this equation number 2, there is no slack variable used. Therefore, this equation number 2 is going to give us a trouble while constructing the identity matrix in the simplex table. That up in equation number 3, this qi square are actually the slack variable which we have replaced by si further, right now? Lambda I si we have it. So these are my slack variables. So this will play a role of slack variable which helps us in forming the identity matrix in the simplex table. But there is a trouble for equation number 2. And we know a methodology if the constraints are giving us a trouble while constructing the identity matrix in the simplex table, which variable we were using? Can anyone tell me?
Artificial variable.
Which variable? Yes, artificial variable we were using. But here also, in this equation number 2, we are going to add the artificial variables so that these artificial variables helps us to construct the identity matrix in the simplex table. Therefore, which will be my basic variable? All artificial variable together with this si slack variable. How many artificials are needed then? How many such a constraint equalities we have in which there is no slack variable? Equation 2 for. How many such we have? N equations, no? J equals to 1 to n. Correct? Therefore, we are going to add n artificial variable in these constraints, which will help us to construct the identity matrix. Then, Wolfe has suggested addition of the artificial variable in equation number 2 type, okay, and construct the objective function. Now, whenever we were adding the artificial variable, what we were going to do? We want to minimize the sum of artificial variable. Correct? No? In two-phase method, we have seen this criteria. So let me write Wolfe in 1959 suggested to introduce the artificial variables Vj, j equals to 1 to n in the Kuhn-Tucker conditions. Let me just rewrite that equation number 2 in the Kuntakar conditions. What is the condition we have written? Mu j plus Cj plus summation k equals to 1 to n Cjk xk minus summation I equals to 1 to m lambda I aij equal to 0. Now this is for j equals to 1 to n. Okay, and we were going to add the artificial variable in these n equations given by the Kuntakar condition and construct objective function. To construct an objective function zv, which is actually sum of the artificial variable. And what is the aim? Whenever we have the objective function as the sum of artificial variable, what is the aim to do this? The aim is to minimize this sum of artificial variable. Okay. Therefore, in step 4, he has suggested to construct a new LPP. Therefore, what step number 4 tells us? Obtain initial basic feasible solution to the following LPP. Now check, we were going to construct a linear programming problem. Means with the help of Kuntakar conditions of a quadratic programming problem, we were constructing a linear programming problem. What is the objective function? As discussed just now, we want to minimize the sum of artificial variable. So what will be my objective function? Minimize ZV, V1 plus V2 plus so on up to Vn. But generally we were writing the objective function in terms of maximization. Therefore, what will be my objective function then? Is it maximize ZV dash minus V1 minus V2 to minus Vn, where ZV dash is minus ZV. Correct, no? Okay, now if you just compare this objective function with the objective function which we have introduced in two-phase method, therefore these two are going to be parallel now. Correct, no? Objective function, if I look at this, what we have done in two-phase method? In two-phase method also, in phase 1, we have given the 0 cost to the original variables and minus 1 cost to the artificial variable, and this kind of objective function is constructed. Therefore, now for this linear programming problem, we are going to use two-phase method. Now, what are the constraints? Let us discuss subject to the constraints. Okay, what is the first constraint? Now, whatever this constraint equation we have written, this is the constant. Therefore, we will shift this constant on the right. We write constraints of a linear programming problem. We are writing the constants on the right side. This here constant right on the right side. Okay. Therefore, here I will just write mu j plus summation equals 1 to n Tjk xk, Tjk xk minus summation I equals to 1 to I and is equal to minus turning 1 to n. Okay, what is the second constraint? Second constraint is actually the original constant itself. Summation aij xj plus qi square is equal to bi again. Right? I equals to 1 to m. I equals to 1 to m. Third is actually minus xj plus rj square. Right? Which actually gives us the non-negativity restriction. Therefore, here we will write all Vj lambda I mu j xj is greater equal by 0 and satisfy. What is extra has to satisfy? satisfying complete condition. Slackness condition. What is the complementary slackness condition? Lambda I si equal to 0, mu j x equals to 0. Now we know I is from 1 to m, j is from 1 to n. Is it okay? Construction of a new linear programming problem. Whatever is the added artificial variable, we want to minimize the sum of those artificial variables. Therefore, the LPP is considered with this format, which are subject to these two types of linearity constraint. Whatever is the third one, minus xj plus rj square. Na? This is actually this minus xj plus rj square is giving us minus xj is greater or equal by 0. That we have included. 7 and 8 also we have taken. 7 and 8 also we have taken here. Right? Lambda is equals to 0. Therefore, the problem is now become solving a linear objective function subject to linear constant with addition to this complementary slackness condition. Okay. Now, in next step number 5, we will say we have to solve this by two-phase simplex method in phase 1 only. Because in phase 2, actually we bring the original cost to the original variables. But here we have this much as the objective function. Therefore, no need to go for the phase 2. Whatever is the solution obtained by phase 1 will be the solution of this linear programming problem. Rather, it is equivalent to the solution of the original quadratic programming problem. Okay. The first step number 5 says that now apply two-phase simplex method in the usual manner to find an optimum solution to the linear programming problem constructed in step 4. Okay. Now, whatever the solution we have obtained, the solution must satisfy these two complementary slackness conditions. Let us write this also. The solution must satisfy complementary slackness condition. Complementary slackness conditions. Okay, and in the last step we will write whatever is the optimum solution obtained in step number 5 will be the optimum solution to the quadratic programming problem also. The optimum solution obtained in step 5 is optimum solution to quadratic programming problem. Now, why this solution to LPP gives us a solution to QPP? Because in the QPP we have to the Lagrangian function, and after constructing the Lagrangian function, the optima of this Lagrangian function is obtained by solving the Kuntaker condition. And Kuntaker conditions are actually the combination of linear and non-linear conditions. Therefore, we are going to solve the linear equations subject to the non-linear constraint equation. But Wolfe has suggested a method to solve those system of linear equations by introducing the artificial variable subject, and he has suggested to construct an objective function minimizing the artificial variable. Therefore, it becomes a new LPP. So whatever is the solution to this LPP will be the solution of actually the optimization of Lagrangian function, and which in turn will be a solution to the quadratic programming problem. And this is what a Wolfe method is. If you have any difficulty in the algorithm, you can unmute yourself and you can ask me. Otherwise, we will go for the examples. Once we take the examples, you will get the idea clear. Yes, students, any problem?
No, ma'am.
Okay. So what kind of strategy is being followed? Let me just explain you in short again. This is what initially we have started with a quadratic programming problem. Then we have constructed the Lagrangian function. Okay. And using this Lagrangian function, we have constructed the Kuntaker conditions. Right. And now what Kuntaker condition tells us? This is a combination of linear and non-linear equations. This is the combination of linear and non-linear equation. Therefore, we have to solve this combination. How we were solving this system of this combination of linear and non-linear equation? We were solving the system of linear equations by taking care with this additional non-linear equation. And whatever is the solution obtained by the Kuntaker conditions will be the solution for the Lagrangian function, right? And this Lagrangian function is actually the unconstrained objective function, and we are finding the optimum value of this, and then in turn which will give us the solution for this constrained quadratic programming problem. So this is constrained optimum. Then what Wolfe has done, by using this Kuntaker condition to constrain programming. That's just how to constrain their programming problem. Because finally, in order to solve this condition, we need to solve the system of linear equations. The system of linear equations he wanted to solve by the simplex method. But if I want to solve the system equation by the simplex method, one have added matrices in order to construct initial solution. Therefore, he has suggested to introduce artificial variable. Once the artificial variable is introduced, he has constrained the linear programming problem with the objective function minimize the sum of artificial variable. Minimizing the sum of artificial variables and which are subject to Kuntaker condition. Once we get the optimum solution to this linear programming problem, hello, there is some internet issue. Let me just
Yes, ma'am.
let me just present my screen again. Have you heard this Wolfe method completely?
No, ma'am. Artificial variable introduce करतो तेवढंच ऐकू.
हो, Wolfe अल्गोरिदम मध्ये तर ते खाली पिंक अक्षरात सांगत होते.
हा मॅम शॉर्ट मध्ये जे सांगत होता ना ते.
अच्छा, लेट मी रिपीट. Hello,
Hello,
Yes,
ma'am.
ma'am.
audible na?
Yes, ma'am.
I hope you have heard this. Okay. What we were discussing from quadratic programming problem to Lagrangian function, from Lagrangian function to Kuntaker condition. Then using Kuntaker condition, Wolfe has suggested the introduction of a new linear programming problem. Actually, the linear programming problem was constructed with the help of introduction of an artificial variable in the system of linear equations. See, I am saying only linear equations, not to non-linear equations. So for the whatever the two-phase method or simplex method we were going to use, while using this method, we have to take care of this non-linear equation. How to take care, I will tell you while explaining the example. Therefore, this is what the journey of solution of a quadratic programming problem. From quadratic programming to Lagrangian, Lagrangian to Kuntaker, Kuntaker to Wolfe. Wolfe has given the method, and then whatever the optimum solution we will obtain by the Wolfe's algorithm will be the solution of an unconstrained objective function, that is a Lagrangian function, which finally will be a solution of our quadratic programming problem. Okay, this is what a short summary is. Therefore, to understand the Wolfe method, you must understand why Lagrangian is constructed, then why Kuntaker condition construction, and then Wolfe algorithm. Okay, any difficulty up to this? Now I will proceed to the example so that the idea will become very clear to you how to solve the system of equation subject to the system of these non-linear equations. Okay, shall I proceed for the example?
Yes, ma'am.
Yes.
The examples looks actually lengthy, but those are quite simple. Okay, let me take an example here. Apply Wolfe method to solve quadratic programming problem. The objective function is maximize z equal to 2x1 plus x2 minus x1 squared subject to the constraints 2x1 plus 3x2 less than or equals to 6, 2x1 plus x2 less than or equals to 4, and x1, x2 greater equal by 0. Now if we look at this objective function, the objective function is quadratic in nature. Therefore, no doubt it's a kind of quadratic programming problem where the constraints are in the linear form again. Let us apply Wolfe method. Let us go stepwise. In first step, we will convert all the inequality constraint, including non-negativity restrictions, to equations by the introduction of slack variable. Okay. Then we will construct the Lagrangian function and Kuntaker conditions. Then we will go for applying the Wolfe algorithm of constructing a linear programming problem. Let us write for first step, writing all constraint in less equal form. Constraint in less equal sign. Why we are writing in less equal sign? Because the non-negativity restrictions are in the greater equal format. Therefore, we will just write it in the less equal. 2x1 plus 3x2 less than or equals to 6. 2x1 plus x2 less than or equals to 4, and minus x1 less than or equals to 0, minus x2 less than or equals to 0. Therefore, how many constraints we have? 4 constraints in all we have. Now we will convert all the 4 constraints to equality by introducing the slack variables. Now, introducing the slack variables. Can anyone tell me which slack variables we were using? Which are the slack variables we were using?
qi square and rj square.
Good. Therefore here, can I write this is q1 square for the first constraint, q2 square for the second constraint, r1 square for the first non-negativity restriction, r2 square for the second non-negativity restriction. With 4 squared slack variables we were introducing. Therefore, what will be the problem now? Maximize zx is equal to 2x1 plus x2 minus x1 square subject to what is the first constraint? 2x1 plus 3x2 plus q1 square equal to 6. Second, 2x1 plus x2 plus q2 square equal to 4. Third, minus x1 plus r1 square equal to 0. Fourth, minus x2 plus r2 square is equal to 0. Right? Now step 3, we will construct the Kuhn-Tucker conditions. To obtain Kuhn-Tucker conditions, what we have to do first? Objective Lagrangian function should be constructed. No? To obtain Kuhn-Tucker conditions, we construct Lagrangian function. Now you have to tell me how the Lagrangian function is constructed. How many variables it will have? First we will write 2 variables original x1 x2, then 2 slack for the original constraint, 2 slack for the non-negativity restrictions. How many Lagrange's parameters are necessary? For first, which Lagrange's parameter we were using? Lambda 1, no? For the second, lambda 2. For the third, non-negativity restrictions, we use mu1, mu2 respectively. Correct now? Lambda I are the Lagrange's multiplier for the original constraints, and mu j are the Lagrange's multiplier we were using for the non-negativity restrictions. Okay? Therefore,
Yes, ma'am.
how many variables we have? R1, R2 I have written. Lambda 1, lambda 2, mu1, mu2. Therefore, see, look, if we have two problem with 2 variable and 2 constraint, these many variables will get involved. Just think, if we have a problem with 4 variables and 3 constraints, how many variables will get involved? Correct, no?
Yes,
Okay. Let us construct Lagrangian function. What is Lagrangian function? First, we have to write the objective function. Objective function is 2x1 plus x2 minus x1 square. Later, we have to multiply all these constraints by the Lagrange's multiplier. One thing you have to take care, whenever we were multiplying by the Lagrange's parameter, your right side must be equal to 0. Therefore, what should I do for this first two equations? We will shift this constant to left hand side, right? And subtract it from the objective function. Therefore, lambda 1 into what is the first constraint? 2x1 plus 3x2 plus q1 square minus 6. Correct now? 2x1 plus 3x2 plus q1 square minus 6. Second, 2x1 plus x2 minus plus q2 square minus 4. 2x1 plus x2 plus q2 square minus 4. Okay. Then minus mu1 into minus x1 plus r1 square minus mu2 into minus x2 plus r2 square. Is that okay? Let me call it as statement number 1. Is the construction understood? Lagrangian function.
Yes, ma'am.
Now we will go for necessary and sufficient condition. What the job we should do for necessary and sufficient condition? Differentiating with respect to original variables x1 and x2. If I differentiate with respect to lambda 1, lambda 2, this will give us the original constant. Therefore, no need to repeat the process. Therefore, the steps we will follow only for differentiating with respect to original variables. Okay, the necessary and sufficient conditions are: first, dou L by dou x1 equal to 0 implies, yes, dou L by dou x1. 2, with respect to x1 we will differentiate. So first bracket gives me 2 minus 2x1, 2 minus 2x1 minus lambda 1 times, correct na? Lambda 1 times, what is the derivative of this bracket with respect to x1? 2. Similarly, the derivative of this bracket with respect to x1 is 2. Therefore, lambda 1 into 2 minus lambda 2 into also 2. What for the third? Minus mu 1 into derivative with respect to x1 is minus 1. Right? And for the last, this will be 0. Therefore, may I write this is minus mu 1 into minus 1. Okay? Equal to 0. Let me just simplify the equation. How I am going to simplify is, let me just multiply throughout by a negative sign. What will happen? This becomes minus 2. Let me shift it on the right. This is 2x1 plus 2 lambda 1 plus 2 lambda 2 minus minus, this becomes plus, multiplying the negative, this is minus mu 1 equal to 2. Is that fine? First equation we have obtained. Second, let us differentiate with respect to x2 equated to 0. Derivative with respect to x2, first bracket 1. I hope I am audible clearly.
Yes, ma'am.
Second bracket gives me 3. Third bracket 1. Therefore, this is minus 3 lambda 1 minus lambda 2. Na? Minus 3 lambda 1 minus lambda 2. Again, this bracket gives me 0. This gives me minus plus mu 2. Plus mu 2 equal to 0. Let me simplify this again by multiplying with a negative. This is 3 lambda 1 plus lambda 2 minus mu 2 minus 1 left is, let me shift it on the right. This gives me plus 1. Okay. Two constants we have obtained. Right? And if I just differentiate with respect to lambda 1 equal to 0, what it is? This is actually the original constant, not 2x1 plus 3x2. 2x1 plus 3x2 plus q1 square equal to 6. And dou lambda 1 by, dou lambda 2 equal to 0. This gives me second constant 2x1 plus x2 plus q2 square equal to 4. Therefore, these are the 4 linear equations in our hand. Now, what we will do? We will define now. Defining what the substitution we were going to do. S1 is q1 square, S2 is q2 square. If I do this, what will happen? The last two constraint gives me the value 2x1 plus 3x2 plus s1 equal to 6, 2x1 plus x2 plus s2 equal to 4. And what are the complementary slackness condition? Complementary slackness condition will be lambda 1 s1 0, lambda 2 s2 0, because j is from 1 to I is from 1 to 2. Mu j x j is equals to 0. Again j is from 1 to 2. Therefore, this is mu 1 x1 equal to 0 and mu 2 x2 equal to 0. Correct na? This format is lambda I si equal to 0 and mu j x j is equal to 0. Now here both I and j runs from 1 to 2. Okay, and finally, how many variables we have? x1, x2, s1, s2, lambda 1, lambda 2, mu 1, mu 2, all are non-negative. Okay, understood Kumtakar conditions? 4 conditions we have obtained linear and 4 non-linear. Means in all we have 8 conditions in our hand. Now in step 4 we will construct the linear programming problem. Rather we will call modify. In these two constraints, we have the slack variable s1, s2 with us. Therefore, only we have to introduce the slack variable in which two? In these two, right now. Let me call this as 1 I have given, 2 and 3. Okay. Therefore, introducing slack variable, we were, sorry, not slack, artificial variable in 2 and 3. Okay. Now, introducing artificial variable v1 v2, the modified LPP becomes what is the modified LPP? This is maximize. Two artificials are necessary, no? Therefore, this is maximize ZV minus V1 minus V2 subject to. How many conditions do we have subject to? These 2, 3, 4, 5. Okay, but in 2, 3 we have to add artificial. The conditions are 2x1, what we have written, 2x1 plus 2 lambda 1 plus 2 lambda 2 minus mu1 plus v1 equals to 2. Let me check. 2x1, 2 lambda 1, 2x1, 2 lambda 1, 2 lambda 2 minus mu1 plus v1 equal to 2. What is the second one? 3 lambda 1 plus lambda 2 minus mu2 plus added artificial v2 equal to 1. And what for the remaining constraint? 2x1 original 2x1 plus 3x2 plus s1 equal to 6, 2x1 plus x2 plus s2 equal to 4, and these are 4 linear constants. And what are non-linear? Lambda 1 s1 0, lambda 2 s2 0, mu1 x1 0, mu2 x2 0. Okay. And no doubt all the variables are non-negative as written in the previous. Now let us go for constructing the phase 1 by 2 phase method. Let me write step 2 now. Sorry, next step. Now we will construct the initial table. Can anyone tell me the basic variables? Yes? Basic
V1,
variables? V1, V2, S1, S2. Right?
yes, ma'am. Yes, ma'am.
Basic variables CB, XB, X1, X2 original, lambda 1, lambda 2, mu1, mu2, S1, S2, V1, V2. These many variables we have. Out of this, the basic variables are V1, V2, S1, S2. What is the cost of these variables? Objective function is 0, 0, 0, 0, 0 everywhere. Na? Only minus V1 and minus V2 is there. Okay. Therefore, what is the cost of these basic variables? CB column. Yes. Minus 1, no cost. Minus 1 for S1, S2 it is 0, 0. What is XB value? XB value
2 2164.
2164.
Good. 2164. Let me write the columns for x1 now. Column for x1 2, 0, 2, 2. Correct?
Yes,
2,
ma'am.
0, 2, 2. Let me write for the remaining also. So 0, 0, 3, 1. For lambda 1, this is 2, 3, 0, 0. For lambda 2, this is 2, 1, 0, 0. For mu 1, this is minus 1, 0, 0, 0. For mu 2, it is 0, minus 1, 0, 0. For S1, 0, 0, third basic variable. Na? S2, fourth basic variable. B1, first basic variable. B2, second basic variable. We can write the columns very easily. What is the value of ZV at this stage? Minus 3, na? CVXV. Minus 2, minus 1. Minus 3. What is the net evaluations now? As this all Cj entries are 0, therefore what were the net evaluations of x1? CBx1 minus 2, right? We will multiply by first two elements of a column, corresponding column. So this is minus 2, here it is 0. This is minus 2, minus 3, minus 5. Here it is minus 3, plus 1, plus 1, 0, 0. What for V1? V1, V2 also 0, 0. Huh? Basic variables. Is that clear? Is the table understood clearly?
Yes, ma'am.
Now we will check which is the incoming vector. Okay, according to our criteria, most negative net evaluation variable will give the incoming variable. But here if I observe, this is minus 5, which is the most negative net evaluation. But as we have discussed already, while solving this system of linear equations, we have to take care of this non-linear equations. Now taking care of this non-linear equations means what? Let me explain. Lambda 1 S1 equal to 0. What actually it gives us? It gives us the idea that both the variables lambda 1 and S1 cannot take a non-zero value simultaneously. One of them must be 0. As the product lambda 1 S1 is 0, means one of the value is always 0. Correct, no? One of the value of the basic variable must be 0. Rather, I can say one of them must be a non-basic variable. One of them must be a non-basic variable. That is, if lambda 1 is there in the basis, S1 could not be entered. If lambda 2 is there in the basis, S2 could not be entered. Reverse also. If S1 is already present in the basis, we cannot enter lambda 1, because if S1 is already there and if we enter lambda 1 and if it both the takes non-zero value, then this condition get disturbed. Okay? Therefore, the meaning of this condition is one of the variable in the pair must take a zero value. One of the variable in the pair must take zero value. Correct, na? Must take zero value, or it is non-basic. Because we know the value of non-basic variable is 0. Therefore, now we will take care of this condition while selecting our incoming vector. According to the definition or the theorems, minus 5 is the most negative. Accordingly, lambda 1 has to enter in the basis. But if we consider its pair, what is the pair of lambda 1? S1 is the pair, no? But if I observe, S1 is already present in the basis whose value is 6, which is a non-zero value. Therefore, we could not enter lambda 1 in the basis. Okay? Everyone getting how we are taking care of these non-linear conditions while solving the system of linear equations, right? Therefore, lambda 1 could not be entered. Let us go for the next choice then. The next negative value, negative net evaluation value is lambda 2, which is minus 3. Okay, but what about its pair? What is the pair of lambda 2?
S2.
S2. But is S2 present in the basis? Yes.
Yes.
S2 is present in the basis with a value 4, means it is having a non-zero value. Therefore, if we cannot enter lambda 2 also. Which two conditions we have taken care? Lambda 1 is 1 0, lambda 2 is 2 0. Correct now? Now what is the next choice with me? Next negative entry. Yes?
X1, ma'am.
X1, mu1.
X1 is the next choice with me. But what is the pair of X1? Mu1 is the pair.
mu1.
But whether mu1 is there in the basis?
No.
No. Means still mu1 and x1 both are non-basic, having zero value. Therefore, one can enter x1 in the basis. Therefore, entering x1 in the basis now. We have selected our incoming variable. This is what the process of taking care of this non-linear conditions. Okay? Is there any difficulty?
No, ma'am.
Good. Now let us go for finding the outgoing vector by selecting a criteria of minimum ratio. Yes. How to select a minimum ratio? xb upon x2. Only provided x1 is having not zero value. Right. Therefore, in this x1 column, second entry is negative. Therefore, let us drop xb upon x1. First entry is 2 by 2, that is 1. Third entry is 6 by 2, that is 3. Fourth entry is 4 by 2, that is 2. Therefore, which is minimum? 1 is minimum. Therefore, this will leave the basis. Therefore, what is my pivot? This is the pivot. Okay. Let me just write a reason here. Here, most negative delta J corresponds to which variable? Lambda 1. Lambda 1. But S1 is already in the basis. Already in the basis at positive level as having a positive value. Na? That is S1 equal to 6 and lambda 1 S1 is equal to 0. Therefore, lambda 1 S1 equals to 0 will not be satisfied if both are positive. Both are positive. This implies lambda 1 cannot be entered in the basis. Lambda 1 cannot be entered in the basis. Therefore, may I write similarly, with a similar reasoning, lambda 2 also cannot be entered. Similarly, lambda 2 cannot be entered in the basis. Therefore, let x1 be incoming. Next negative net evaluation we have taken care. Right now? What is the next step then once we obtain the pivot? Convert this pivot to unity, remaining entries to 0 with the row operations. Which row operations one should use? R1 by 2, R3 minus R1, R4 minus R1. Is it okay?
Yes, ma'am.
Now what I will do, as the table will not be in front of me, I will write the table directly. Okay, resulting table. You should practice on your own. So this is the first iteration one can see. Basic variable CB, XB, X1, X2, lambda 1, lambda 2, mu1, mu2, S1, S2. Now, as we have discussed already, as this V1 as an artificial variable is going to leave the basis, you can drop the entries in the V1 column. Therefore, here I can write simply V2. If you write V1, there is no problem. which are the basic variable. Instead of v1, now we have x1, v2, s1, s2. Cost will be now 0, -1, 0, 0. By performing the row operations, I'll write the entries directly. x2 will be 0, 0, 3, 1. Lambda 1 will be 1, 3, -2, -2, 1, 1, -2, -2. This is -5, 0, 1, 1. For mu2, this is 0, -1, 0, 0. For S1, this is 0, 0, 1, 0. For S2, 0, 0, 0, 1. For V1, one can drop the entry actually, or if you want, you can find 0, 1, 0, 0. Okay, let me write the CJ entries as well. 0, 0, 0, 0, 0, minus 1, minus 1. What is Z? Let us check. Is it -1 now? CBXB. Previous table gives me -3. Now we have obtained -2. Value is increased. Let me find the net evaluations. 0, 0, -3, -1, 0, 1. For S1 is 2, 0, 0. For here I am going to drop. For V2 it is 0. Okay, let us repeat the process. Which is the most negative net evaluation again?
Lambda
Lambda
1.
1. But still S1 is there in the basis. Therefore, we cannot enter it. Next net evaluation is next negative net evaluation is lambda 2. But again, its pair S2 is in the basis. Therefore, we cannot enter it. Right now. Then remaining all are non-zeros. Non-negative rather. Okay. Remaining all are non-negative. But the solution is not optimal. Still we have to carry out the process. Anyhow, we have to enter one of the variables. So what we will do, as we look at the remaining net evaluations, all are non-negative. Where the negative entries we cannot enter lambda 1 and lambda 2. Therefore, what we will do, we will try to enter the original variable x2. We will try to enter the original variable x2. If x2 is entered, let me check which one is going to leave the basis by calculating xb upon x2. By calculating xb upon x2. If I look at x2 column, first two entries are 0. Therefore, let me drop first two entries here. xb upon x2, 4 by 3, 2 by 1. Which variable is going to leave the basis? S1. Right now? 3 is the pivot. Clear?
Yes, ma'am.
3 is the pivot. What is the next step? Here what we will do? As lambda 1, lambda 2 cannot be entered in the basis, let us introduce x2. Why I have not introduced the remaining variables? Because we want to find the values of the original variables. No, therefore we are going to introduce x2. Okay. Again, what to do? Converting pivot to unity, remaining to 0. Let us write the table again. Which are the basic variables now? V2 is there already. Instead of S1, now we have X2. Its pair S2 will be there. Cost will be 0, -1, 0, 0. XB column gives me the value 1, 1. You can just check the entries afterwards by doing on your own. I'm writing directly now the entries. Because one can find out the entries if the previous table is in front of your eyes. Right now? I've written all the entries now. Which variable I forgot? V1, V2 I forgot. Now here V1 is already dropped. If it is dropped, you no need to write also. V2 I can write directly. Which entries are? Let me check the cost. Cost is again -1. There is no change. Let me write the net evaluation 0, 0, -3, -1, 0, 1. This one is to 0, 0. For V2 it is 0. Now let us check which variable I can enter now. Which is the most negative?
Lambda 1.
Lambda 1. Whether it's pair S1 is in the basis? No, it is not. Correct now? Now we can enter lambda 1. So this will be my entering vector. Let us check which is the leaving vector by calculating minimum ratio. Okay, the minimum ratio will be calculated. Which variable is going to leave the basis in this case? These two are negative. xb upon 1 by 1, 1 by 3. Na? 1 and 1 by 3. This will leave the basis. So which will be the pivot? This one will be a pivot. Let us do the operations again. Converting pivot to unity remaining entries to 0. Let me rewrite the table. Actually, this variable lambda 1 is trying to enter from the first iteration, from the first table itself. No, finally it is entered in the basis. Correct, no? Let me write the basic variables now. x1, lambda 1, x2, s2. Cost is 0, 0, 0, 0. xb values are 2 by 3, 1 by 3, 14 by 9, 10 by 9. x1 is 1, 0, 0, 0. x2 0, 0, 0, sorry 0, 0, 1, 0. Lambda 1, 0, 1, 0, 0. Lambda 2, 2 by 3, 1 by 3, minus 4 by 9, minus 8 by 9. Mu 1 is minus half, 0, 1 by 3, 2 by 3. Mu 2 is 1 by 3, minus 1 by 3, minus 2 by 9, minus 4 by 9. S1 is 0, 0, 1 by 3, minus 1 by 3. S2 is 0, 0, 0, 1. V2 is minus, V2 is removed, no? Therefore I can draw. And the net evaluations are Z is 0. Net evaluations are also 0 for all the variables. Here all delta j's are non-negative. Let us stop the process. Okay. Therefore, what is the final solution? Yes. Final solution. X1 star. What is the value of X1 star? Star is the value. X1 star is 2 by 3. X2 star is 14 by 9. 2 by 3. X2 star is 14 by 9. The value of objective function z is 0 is actually the objective function of a linear programming problem. But we want the objective function value of the quadratic programming problem. Na? Therefore, what we will do? We will substitute the values of x1 and x2 in our original objective function. And what is zx then? Yes, what is zx? 2x1, that is 2 into 2 by 3, plus x2, that is 14 by 9, minus x1 square. No? Therefore, this is 2 by 3 bracket square, and this gives me 22 by 9. And this is the solution. Yes, any difficulty in the Wolfe method? If you have, you can ask them. Solving this QPP by this linear programming method is very easy. Linear constants you have to write. You have to write the simplex table as well. But while selecting an incoming vector, you have to take care of these non-linear complementary slackness conditions. There is no other role of these complementary slackness conditions. And whatever the final solution you will obtain for the values of the variable, put the values of the variable in the objective function of the quadratic programming problem, and this will be your final optimum basic feasible solution. Yes, any difficulty regarding this, you can ask me.
No,
Already
ma'am.
we are 15 minutes late. Okay. Just make a revision for this lecture. If you feel any kind of difficulty, we will take one more lecture, one more problem on this. Okay. Let me stop for today. Thank you for being with me for today's lecture.